Okay, so for the last talk of today, this session, we have Chia-Yu Chang from Toulouse, and we're going to be talking about border Subrank higher.
Thank you. And thanks the organizer for this wonderful workshop and giving me this chance to talk here. And we already saw many quantity that's associated to a tensor, like tensor rank, border rank, asymptotic rank, also some varying rank about polynomials. And today, here I'm going to talk about another measures of tensor. It's called border subrank of tensors. And especially I'm interested in the border subrank for higher order tensors, for the structure tensor for the for algebra. Okay. Okay, now let's start from the matrix rank. Because border subrank is also a generalization of matrix rank. And for a matrix, there are several methods to find its rank. And here I list two methods. Okay, the first one is that the rank of a matrix is the minimum integer r, such that a matrix can be written as the sum of r rank 1 matrix. And another method is from applying row and column transformations on a matrix and to make it diagonal. And the number of non-zero diagonal entries is the rank of the matrix. And this first method is generalized to the tensor rank. And so if a tensor T, the minimum integer r such that tensor T can be written as the sum of r rank 1 tensors, then this r is minimum r is the rank of the tensor. And for this case, how can we generalize this to a rank of a tensor? Here we have diagonal matrices and what is the diagonal and how to compare it in tensor case. And for this first method, we can see like those rank 1 tensors, you can write them into some linear map phi 1 of vi and phi b of vi, where those phi j are from CR to bj, and then okay, and then we can rewrite it as the tensors of those linear maps on this sum of the tensor product of EI, and here we call this the diagonal tensor. Then we can use this to compare with this tensor T, and this generalized this method for finding matrix rank. And this diagonal tensor is just the unit tensor or GHZ state that we have heard in these talks. Okay. And then now, for comparing, we use the restriction and the degeneration. It's the same as we heard in previous talks. And if we have two tensors with same order, then we say S is the restriction of T and denoted by this. If that S can be written as the by applying some linear maps on T, and we can define degeneration is denoted by this. That if S is a degeneration of T, if S lies in the closure of tensors that are restrictions of T. Okay, then now we have diagonal and we have comparing, so we can use this to define rank and the subrank. Okay, then this is the definition. That's the rank of T is the minimum integer r, such that T is T is a restriction of the size r diagonal tensor or unit tensor. Okay, and so similarly, we can use degeneration, and this gives us border rank. And these definitions are the same as the rank and border rank definition that we have heard before. And then the subrank and border subrank, we also use diagonal tensor to compare with the tensor, but we switch the position of our tensor and the diagonal tensor. So the subrank is the maximal integer r, such that the size r in tensor is a restriction of t. That means that the r is the maximal size of the diagonal tensor, such that we can obtain by applying linear transformations on t. Okay. And similarly, we can use degeneration to define border subrank. Okay. And there are some properties of it. If we first for b equal to 2, for order 2 case, matrix case, those are the same as the matrix rank. And then if we consider the diagonal tensor, then all these values on the diagonal tensor are equal to the size of the diagonal tensor. And from the definition, we have there's an order between these quantities. That subrank is less than or equal to border subrank, then border rank, then rank. And for rank and border rank cases, only for the concise tensors that has a lower bound equal to related to the dimension of vi, and but for subrank case, all tensors the border subrank and subrank are lying between 0 and the minimum of the dimension of those vector spaces. Any question about the definition? And now I want to talk about motivation, why we care about border subrank. Here I list 3. And border subrank is subrank and border subrank are first introduced by Streisand in studying the multiplication of matrix. The complexity of matrix multiplication. And Streisand, there's a method called laser method, and that is used to finding upper bound of complexity of matrix multiplication. And it's used as some intermediate tensors. And so far, the intermediate tensors that has been used to find upper bound on the exponents has low subrank or border subrank. So we say that those intermediate tensor faces some barriers, and that barriers is in fact related to subrank and border subrank. And another motivation is from quantum information theory. We have seen in Michael's talk about the SLOCC is the same as restrictions and the border subrank in quantum information theory measures the rate at which the entanglement of GHZ type can be distilled from a quantum state. And here the GHZ type is the same as the diagonal tensor here. And also the asymptotic rank and asymptotic subrank has the form the same as the capacity of a quantum channel. Okay. And the third motivation is from combinatorics, that the border subrank can give an upper bound on the hypergraph independence. This is useful, for example, in cap sets problems, sunflowers problems, or commonness problems. Okay, now I want to talk about structured tensors of algebras. Let's A be a finite dimensional unitary algebra over complex numbers. In our paper, we also study algebras, the algebras, or not unitary algebras. But in this talk, I will focus on this. And for k greater than or equal to 2, we define the case structured tensor of algebra A, which is a tensor lies in A tensor of the the case tensor power of A dual, and it is given by this multilinear map, which is given by the multiplication in the algebra. Okay, and why we studying this stressors when studying complexity of matrix multiplication tensor stressors determine the asymptotic subrank or set of several algebras like matrix multiplication that is used to define the structure tensor of this is used to define complex exponents of matrix multiplication, and also the upper triangular matrix multiplication is also used, and the structure tensor of truncated polynomial algebras, and the structure tensor of neural algebras, and the Stresson studied this for order 3, so it's the second structure tensor. But in our paper, we studied for higher order case. Okay. Okay, and so now I want to talk about some test results about structure tensor. So Blaze in 2016, Blazer and Liskov proved that the tensor degenerations are algebraic degeneration. It states like this, that if we have S, tensor S, that's in A tensor A dual, with unity property, that means that the unity, the one in the algebra A, S of 1x is equal to S of x1 equal to x. Then if a tensor lies here satisfying this, then we have that the degeneration is equivalent to the algebraic degeneration. So when we define degeneration, we apply linear maps on each vector separately. But this theorem tells you that you can just use the same action on each vector to get this degeneration. Okay, and then so this is for order 3 case, and there are more higher order structural tensors that are studied in 2023 by Blazer, Mayer, and Schinch. And there's a fact that in their paper that the rank of the case structural tensor is less than or equal to the rank of k plus 1 structural tensor. And also they proved a multilinear order Stresson theory. And this theorem was originally in order 3, and they proved that it's for higher order. They generalized this to higher order case. So if T is the number of maximal two-sided ideals in A, then the rank has a lower bound related to this T, which is k times the dimension of the algebra minus k minus 1 times T. Okay. Okay. Now, because we are interested in broader subrank of those structured tensors, so recall that the definition of broader subrank and the border rank are used the degeneration. So we want to study the degenerations between structured tensors. Okay, not less this diagonal tensor is actually also a structured tensor, and is given by the algebra C to the R, where the multiplication is multiplied coordinately. And so we can look at how to compare to the structured tensor of two algebras, and that helps us to find broader subrank. And let's A and B are two unital algebras. Then if the structured tensor if K not structured tensor of A and B has a degeneration, then for all k less than or equal to k naught, we also have degenerations between these two structured tensors. Okay, and immediately conclusion from this theorem is this corollary that the border subrank of the k plus 1 structured tensor is less than or equal to the border subrank of the k structured tensor, and this is by a definition of border subrank and border rank. And also for border rank, we also have these inequalities. And this is by for this inequality is by taking let's b to be the c to the r prime, and then we can apply this theorem and get this. Okay. Okay. Now, so in our paper we determined some the border subrank for some algebras. And here I will list some methods that we used for finding the border subrank for tensor T. Okay, so for the lower bounds, by definition, we can just construct restrictions and degenerations to unit tensor, then we get a lower bound on the border subrank. Okay, okay, thank you. And for upper bounds, first I want to talk about two ranks. First is geometric rank, and this is often used to get upper bound for border subrank, and it has an upper bound is the minimum of the dimension of Vj, and in the case that when the geometric rank is maximal, that is equal to this minimum number, then and we can and in that case, if it's hard to find to construct a degeneration for the lower bounds, then we will consider another rank called G-stable rank, which is introduced by Ham in 2022, and this lies in between border subrank and the geometric rank. So if geometric rank does not work, then we will use this G-stable rank. Okay, and there is another two methods. Actually, there are more methods in our paper here. I just list some. And another two methods, one called an invariant theory. One is from invariant theory. If for all tensors S in this space, that is a restriction of T, has this property that it is unstable under the SL action, which means that the zero lies in the closure, OB closure of S under the action of SL. Then in this case, we have that the border subrank of T is less than R. That is because the unit tensor is not unstable under this action, and also this condition is a closed condition. So from this result, we get that the unit tensor is not a restriction of T, and because this is a closed condition, so we also get that the unit tensor is not the degeneration of T. Okay, and another method we used is from border rank. So if there exists some tensor S with the border rank of S is equal to R, and let S is not a degeneration of T, then the border subrank of T is less than R. So if border subrank is greater than or equal to R, then the size R unit tensor will be a degeneration of T. Then, and because the border subrank of S is R, so the size R diagonal tensor would also be S would be a degeneration of lost diagonal tensor. Then we will get T is a degeneration of that diagonal. Yeah, then we won't have this, so this gives us a contradiction. Okay. Okay, now here I list some results we had. For commutative algebras, a commutative algebra can be written as a direct sum of local algebras, and so their border subrank of their structured tensor would be bounded by the border subrank of those local algebras. So we only consider the local algebras here, and here we consider three commutative algebras: the linear algebra, and the truncated polynomial algebra, and this QN algebra that is a generalization of the CW tensor. Okay, and here I use the green pen to for the lower bounds of those quantities for the method of the lower bound we get. Here we just get this by by constructing a restriction on the size 2 unit tensor, and the upper bound here is by a geometric rank. And this one is by constructing by using the invariant theory that we have some let's for all tensors in the restriction is not stable, so we have this. Okay, also we have some results on the algebra of matrix multiplication and the triangular matrix multiplication, and those are the methods we use. Okay, and stop here. Thank you for your attention. Yes.
The case of symmetrics.
Yeah, we did not look at symmetric subrank. Yeah, but you can still define its symmetric. And sorry, could you say it louder?
The examples you gave.
The example. I don't know.
No, I mean, if you go to the previous slide,
yeah.
If I guess the first one is not, the other two are stars.
Yeah.
The first one is just a 5 point order.
But then it's the same behavior as the Einstein.
I mean, it depends on what you mean with behavior.
Like the number in front.
Yes, these are all suitable. So the border rank is always key. The border rank is always the dimension of that. And the border subrank is something strange. It's here. How there is two, because there is a bound that comes from that usually when this number is very small, it's because the socle of the algebra is very small. And the fact I think it's either for the first one it's 2 and for the other it's 3. Unless it's because of that's because of the socle. That's the property of the socle. The degree of the socle, not the ranks. What gives you guys think that the socle? And it's also where the socle is. Any other question?